Now let's find out the frequency response of the common source amplifier on multisim. Now notice that we have labeled two nodes V0 and Vsig. The analysis proceeds in a slightly different way. Instead of directly simulating, we first need to define some parameters. So we go to this part here, simulate, analysis, and AC analysis. Now you can see on your screen f-start, f-stop, sweep type, number of points per decade, vertical scale. Now let me explain to you what they are. F-start is the start of your x-axis. Remember, it is in hertz, and f-stop is the upper limit for the x-axis. Now what is sweep? Sweep basically tells you the gradations that you are going to have on your horizontal x-axis. For example, we can have decades, which means that you are going to have gradations that are going to differ with each other by a multiple of 10. If you have octave, they are going to differ with each other by a multiple of 8. And if you have linear, then they are going to differ with each other by an increment of 1. So we choose decade. And on our vertical scale, we are going to have decibel. We have other options, linear, logarithmic, and octave. But remember that we have been making our graphs with decibels. So we are going to have decibel here. Now moving on to the next part, that is the output. We see that a list of variables is provided on the left side of the dialog box. Now this basically shows the variables available to us for which we can perform the AC analysis. Now you might have guessed from the previous tab that 1 Hz to 1 GHz are the frequencies over which we are going to simulate our circuit. Even though if you look closely here, we only have a signal of 1 kHz. That does not matter. Why? Because bandwidth is independent of the frequency of the input signal. So 1 Hz to 1 GHz is pretty suitable, and we are going to find our quantities that we are going to measure, and we see that V0 and Vsig are separate quantities. Now if you remember from our previous lesson, we had on our x-axis V0 divided by Vsig. So we are going to make that expression. We say add expression. Now here we are going to select V0, copy variable to expression. Here we are going to select slash, which means divide, copy expression, and here we are going to select Vsig. And here we have the required expression V0 over Vsig. We press OK and we simulate. Here we are. We have two graphs. The first one is the magnitude graph and the second one is the phase graph. And let me delete this one. I click on it and I click on delete, and here we are. So we want to change our background. We simply click on this and our background is white. Now you can see on this circuit that the bandwidth is quite reasonable. But still it would do us good to find a good approximation for the bandwidth. So how do we find that? Now let me teach you how we are going to do that. This is a cursor. We get one when we click on it. And if you move it, the required values are going to change here. Now let me move it. And you can see some of the quantities are moving, namely x2 and y2. Now y2 is basically the required magnitude V0 divided by Vsig. If I place the cursor here, so you can see that this is indeed what I'm talking about. And the maximum value here has reached 31. And we are going to continue that, and Now the value starts to drop. So in order to find the bandwidth, we need to find the value of the frequency at these points. We remember that FL and FH are points at which the midband gain drops by 3 dB. So approximately they will be here. This is approximately FL, and our value here is 60.5909. And when we move forward to find FH, we see that the value is 921.5230K. So our bandwidth is approximately 850-860 kilohertz. So it's quite reasonable. This simulation was to demonstrate to you how your circuits written on paper can be translated to the software, where you can see through the simulations whether your circuit is going to perform in real life or not. So we close it here and we go back to our circuit. Now I urge you to practice this on your own.